just look into a typical FTIR spectroscopy, okay, typical spectrum will look something like this, okay. On one side, you can see this is actually transmission line, okay. It is basically nothing but transmission line, okay. So you can see it's written transmission actually on this side, okay. And on this side, it's wave number. So wave number is just the reciprocal of the frequency part, right? So this actually can be done, okay, and then you can actually understand this. And when you look into a typical spectra of an FTIR, it will look something like this, okay. Ignore whatever text is written here. There are different ways of analyzing it. But what exactly it gives me is the functional group that is actually present in a system. For example, you have synthesized some sample, okay, and maybe you have used some alcohol, you have used some acid, okay. After the synthesis, whether those kind of bonding are still there or not, this is something which is very important in order to determine the purity of the sample, okay. And for doing that, we can actually use FTIR spectroscopy. Apart from that, let's say it's some kind of metal, okay, and you want to know that what kind of metal the system has, then probably you'll be having some wave number and some peak in the lower frequency range, which is below 600 or below 500, okay. In this range, you're actually giving the metallic bond. So suppose you have synthesized tin oxide using some chemical, some acid, okay. Most of the time you're going to get this, okay. And this OH might represent the amount of water bond that is present. So if you are using an acid or a base, okay, or even if you're using some solvent which has got some water component, and if it is present in a large amount, you will actually see a broader peak, okay. So this is something which is seen in FTIR spectroscopy, okay. So today whatever we are going to do is actually nothing but more of text, okay. Try to understand the details of this FTIR spectroscopy, okay. So what I'm going to do is, as always, we're just going to write down a few important points, okay, which are important, okay. So what does this spectrum exactly represent, okay, why we are studying this and so on, okay. So these things are something which we're going to see. So the spectrum, okay, spectrum represents, okay, the molecular. So you can actually take a molecule, okay, and take out information about the atoms that are present in that particular molecular system. Okay? So spectrum actually represents the molecular absorption and transmission. Okay? So if I say that an IR radiation is incident on a sample, and that particular sample is made up of atoms, how does the atom react to that particular IR radiation? Of course, it will start vibrating, okay, and as it vibrates, it is going to emit some energy, and if we can actually study that energy, that will actually give me the information about that molecular system. So in general, whatever we are going to know from FTIR spectroscopy is basically a fingerprint of the sample. And fingerprint is something which is unique to a sample. So every time you take up tin oxide, every time you take up a polymer, the FTIR that you're going to get is going to be similar, okay. So the position of that peak will be same. Might be it will be slightly lesser or more depending on how much amount is present, but then the peak position won't change, okay. So in general, we can say that if we are considering two different compounds, okay, it will basically produce the same. No two different compounds will produce the same spectrum. So if it is a different material, you're not definitely not going to get the same spectrum, and that is actually nothing but the fingerprint of that particular material. Okay? So that's why it is very important. So most of the things, let's say for example, you take a UV visible spectra. Now, when you look into an UV visible spectra, two different elements, might be the elements are different, but the chances are they might be having a similar band gap. Okay, the chances are they might be having a similar peak position. Okay, so UV visible spectra cannot really tell you what kind of element we have. But then, if we look into FTIR spectra, that is definitely a very good gives you more information about the property of that material, and it can also help determine the exact material. Okay? So FTIR provides the following. So if you do XRD, you know what kind of material it is. It also has got some peak position, which is actually can be called as more or less a fingerprint. But then in FTIR, you are really not sure. In XRD, you are really concerned about more about the crystallinity and other information parameters. Okay. Here, the crystallinity is secondary. The important thing is what are the functional groups that are present. Okay. It's very important. It's a very important tool in chemistry. But nowadays research is interdisciplinary. So even if you are in physics, you are developing some material, you need to know its chemical properties. So definitely you need FTIR. Okay. So every research is becoming interdisciplinary now. Even if you are not very comfortable with chemistry, at some point of time, if you are doing research, you need to understand certain points from chemistry point of view. So what are the information that it can provide? Okay. So it can identify a known material. So there is a list and you have peaks and you see that this peak position might be because of the OH group, let's say, for example. So even if you don't know the material, if you see a peak there, you can say that there is a material which is unknown to you, okay, and that must be having some OH function present, okay, and then it can determine, okay, determine the quality or consistency of a sample. So you are synthesizing a sample and you are expecting certain material to be more in amount, okay? But when you do the FTIR, you see that the peaks are very small. So that means the amount of that particular element is very less, okay? So that is not the quality that you want. So it can actually help you to determine that quality or consistency of a sample, okay? This is okay. So what usually happens is that we can actually find out the quality and the consistency of the sample. Okay. The third point that is important is it can determine the amount of components. Okay. So might be you will actually synthesize a sample which is a compound and not a pure sample. So how much amount of a certain component is present? Okay. It can also be determined by this. So it's a very important tool, and nowadays with so much research going on, we can actually say that this can be used as a confirmation technique to know whether whatever sample you have actually synthesized is pure or not. Okay. So let's just talk a bit about the IR spectrum that we have. Okay. I'm not going to talk about the laws or the rules, okay, which you already know, because we have already talked about that. We're going to just talk about some other details about infrared spectrum, okay. So, there is infrared spectroscopy. That means you allow infrared radiation to fall on a sample. And as you already know, there will be vibrations involved. And then finally you detect it with a detector and then you analyze it. But then what I'm saying is FTIR, Fourier transform infrared spectroscopy. How is it different? Okay. How does an infrared spectrum takes up so many frequencies together and puts them together in a graph? That is something which is more important to understand. Okay. So for that, we won't go to FTIR first. We will first go to IR spectrum. So, IR spectrum is basically an old technology. It's an old technology. Okay. Nowadays, it's mostly FTIR. Okay. And there is basically something which we call as dispersive type. So I hope all of us understand what is dispersion. So whenever someone tells you, see, I have taken this answer a number of times from the student that whenever I ask that, okay, why does white light split into 7 different color? What is the process called? I have even heard people saying mm, scattering, okay, and then maybe diffraction, all those kinds of ideas. But this is something which is not in your class 7 and 8, and it is not dispersion. It is dispersion. What is getting dispersed here? The wavelength and the frequency component are getting separated, and that is what is called dispersion. So in IR spectrum also, we have something which we call as dispersion. So in order to disperse a signal into its component frequency or component wavelength, what do we need? We need a prism. Okay. And if you have something better than prism, which can actually differentiate these frequencies better, it's even better. So in modern dispersive technology, it's grating and not a prism. Okay, that's what the use of grating is all about. Okay. So what happens is we have separated the. You understand this because this is important for the theory part. So what happens in this dispersive type? We actually separate the individual frequencies, okay, of energy emitted from the IR source. So you understand that what do you mean by energy emitted? You know frequency means you have no energy. So that means if it's separating the frequency, that means you are also separating the energy. Okay, so it's quite logical and connected. Okay, and how do we actually do it? Okay, this is accomplished, we can say, okay, by this is actually accomplished by use of prism, as I said, or grating. So we will use the prism or a grating to accomplish this. Okay, and please understand this is same as dispersion of white light. So this is the same logic that we are actually having here. Okay, it should not be very difficult to understand. Okay, so that's very important. But then why grating? Why not prism? Because if there are 10,000 lines per centimeter, okay, it will actually separate out the frequency component more easily compared to something like a prism. Okay, and that is why we are actually going to use a grating. Okay, so what happens usually is this grating separates, okay, the frequency better, the frequency better. So you will have a better separation of the frequency using the grating. So that's why this grating is good technology. So modern dispersive technology uses a grating. Okay. So even if you are using something in the lab, okay, maybe an optical bench to do some kind of optical experiment, you use a grating. Then what happens is this separated signals from the sample will actually reach the detector. Okay, and then what happens is detector measures the amount of energy, right? So how much energy has reached, it will measure at each frequency. You have to understand this. So you have an input signal, okay? Oh, let me just do this schematic and just probably rub it off again, okay? So you have got this IR radiation, let's say, okay? And then you are actually putting a grating here, let's say, and then you are actually having a separated frequency, okay? And then this is your sample. Let's say this is your sample. Okay, and some of the energies will be absorbed here, some would actually just cross through. So whatever crosses through, okay, might be weaker, okay, might be weaker or might be stronger, and this will be actually finally in the detector. So this is your detector, this is your sample, okay, this is probably a grating, and so on. So you have a IR sample, grating separates the frequency, it falls on the sample, and then finally it is getting detected by the detector. So at each frequency, so this is one frequency, this is second frequency, this is one frequency, this is second frequency. So let's say this is the first energy, this is the second energy, okay? And these energies are dependent on what is the individual component of the frequency, okay? So this is what is meant here. So I'll just write down the sentences and I think this will be clear to you. Okay? So this is just for example. I think you understand this. Not very complicated. So the detector measures the amount of energy at each frequency which has passed through the sample. Okay? Which has passed through the sample. Okay. So this is important again. And then after we have this information, what we do is we usually plot. And what we plot? We actually plot the intensity versus frequency. So we actually plot a graph of intensity versus frequency. And that's very important. So once we plot the graph of intensity versus frequency, we can actually get the information, and that is exactly what is getting plotted here. Okay? So that is important. So next is some more points, okay? And when we do this technology or use this technology you to get information about the sample, this FTIR is actually provides better information. So I talked about IR spectrum. Let's talk a bit about FTIR now. Why FTIR is preferred? So FTIR preferred over dispersion, okay, or filter method. We can actually say dispersive, okay, oblique filter method, okay, for the following reason. So let me just write down some point because of which FTIR actually provides you better information, okay. Reason, and let me just take up one by one. Number one, non-destructive technique. So most of the times when we do a characterization of a sample, if it is non-destructive, we prefer that. What do I exactly mean by non-destructive? It means that once I actually have let a sample under an XRD or an FTIR spectroscopy, the sample is going to give me the sample that I've used. I can reuse it for any other characterization also. Okay. So I do FTIR the sample, and then I after I get the spectrum, I take the sample out, and then again I use it for XRD and so on. Okay, so it's a non-destructive technique. Okay, so you're going to have a better view. Then it's a precise measurement. Usually the spectrum that you get, the peak position that you get is actually quite precise. Okay, and then it is having an increased speed rate. So the speed at which an IR spectrum is obtained, if you're using an FTIR spectrum, okay, FTIR device, you are going to get the spectrum at a very fast speed. You are going to get it better. Okay, you are going to get it the faster speed. The speed rate or the scanning rate is quite high without compromising with the quality of the spectrum. Okay, and then of course increased sensitivity. So using an FTIR, you can actually divide that incident infrared radiation into a spectrum, okay, into different components of the infrared system, okay, and it can be divided or separated much better compared to the conventional IR spectroscopy. Okay, so let's say we are actually having a 1 second scan, okay, and we can actually have that 1 second scan simultaneously, okay, and we can actually add them up, okay, and if we add them up together, we can actually cancel out the noise, because if it's a IR spectrum flowing through air, flowing through an environment, flowing through an instrument, there will be a lot of noise. So in order to separate out that noise, if we can have more signal from the sample, we'll see a better peak compared to the noise. So we straight away know that this is because of the sample, and whatever noise is there will be very less compared to the signal from the sample. So once again can be added together, okay, to ratio out random noise. Okay, so it has started raining here. I know the weather, because of this probably the internet gets cut off. So I hope, let's see how much we can continue. Okay, so if we just talk about FTIR, it is basically nothing but the same method as IR. Okay, it is basically the method for measuring the all IR frequencies. That's important. IR frequencies. Okay, and we are not going to have a small range. We are going to have a larger range. Okay, so all other frequencies rather than individually, okay, as in dispersive method. So even if you consider white light getting spread into 7 different colors, we are just talking about VGO. But even red has got different frequency ranges that is not getting separated in that prism technique. Okay, if you use grating, definitely you can see that variation. Okay, but then if you use an FTIR spectrum, okay, if you are going to see that, you are going to see much more variations compared to a standard dispersive method. Okay, so what exactly happens in this particular technique is we are going to again have two beams as always. Okay, so what we have is here this. Okay, let me just write down this. We are going to actually use a beam splitter, and you can use a beam splitter as we have seen in the UV visible spectra to actually separate out the noise. Okay, and from that beam splitter we are definitely going to get two beams. And what are those two beams going to give the information about? Okay, So the first beam will basically having a fixed length, one fixed length. So that means that out of the two beam, one beam will actually follow a fixed length. There is going to be no variation, okay? But the other beam will actually follow a variable length. One fixed length, variable length. Okay, I should just write down variable length and not one. Okay. The other beam is going to follow a variable length. So if you just vary it in that way, you are going to have a different frequency range, okay? Variable length. So how is this variable length done? By using mirrors, okay? Variable length, we are going to get it because of mirrors. So for one part of the beam, it's going to just go straight, which actually measures any kind of noise that the system might have. And the other one, there will be actually a variable length. And how do we vary the length? By using mirrors. We use mirrors, and with the mirror, the length can be varied, okay? And then finally, both of them will meet at some point, okay? They will actually meet, okay? So what happens is, when you can also use a similar idea to write it down in your exam, when they finally meet. So in optical term, we say interfere, right? So when they finally interfere, they are going to interfere, okay? We actually get something, which is called a interferogram. Interferogram. So you know, you will have a constructive interference, destructive interference. Based on this, you are going to get a spectrum. But then this is the term. The question would be, what is an interferogram? For 2 marks probably, okay? So if we have two beams, okay, let's say in a FTIR system coming and interfering at a certain point, we are going to get an interferogram, okay? So what is this interferogram is all about, okay? So that is important. So you know how are they formed and what exactly, what kind of information are they going to provide me. Okay, so let me just write down one line here. It is basically nothing but a unique property, okay, at every point, okay. So it's a unique property that every point. So what is this property dependent on? It is dependent on the movement of the mirror. So it is basically a function, okay, of the moving mirror position, okay, which makes up the signal, okay, and has information, okay, about every IR frequency which comes from the source. Okay, so what happens is, if the mirror keeps on moving to and fro, okay, there is going to be different frequencies. So at different frequency, it means different phases, okay, and they are going to interfere constructively with the fixed length of the beam that is coming, okay, and those phases will actually separate out all the frequency component of the IR spectrum, okay. For this, you need to have a very clear idea of optically aspect you might be having, because these ideas are already given in your class 11. So please just check it once, okay, but I think it's not very difficult to understand. Just put some logic into it, okay. So we have the mirror, it will keep on varying the length. That means it is going to vary the phase of that particular frequency range. And based on that, that particular frequency range will be incident on the sample. And finally, when it comes and meets the original length of the beam, it is going to give me a signal which can be separated out from any kind of noise the system might be having. Okay, so just try to understand it. Okay, might be it will take some time, but I don't think it's very difficult to understand. Okay, so I hope you can actually take some time and try to understand this. Okay, so what happens is, this measured interferogram, okay, cannot be directly interpreted. Okay, you need to convert it into a human readable signal. Okay, and that actually can be done by with the aid of computers. Okay, we can actually do it. Okay, I hope we can just finish this topic. Okay. So this measured interferogram, okay, let me just write down the technical term, cannot be interpreted directly, okay. So you need some computer aided program, and for that the best is Fourier transform. So you know Fourier transform can basically help you to change the domain. Let's say you are converting it from a time domain to a frequency domain, okay, because you know whatever signal you are getting with the help of that moving mirror is based on time, okay, and you can actually convert it into a frequency domain, and that is something which can be actually done with the help of an FTIR spectrometer. Okay, so basically it's nothing but a programming system that we have. It's a mathematical code. Okay, so decoding in the visual frequency is required. So you need to have a very clear idea about the the Fourier transform. Okay, but then for now you can see that this actually has an importance in the practical field is required. Okay, so that's the first thing. And how do I decode it? This can be achieved by Fourier transformation. So I can use Fourier transformation actually to get the signal getting decoded. Okay, so in general, okay, let me just give you a very simple schematic here. So in general, maybe if you are not decoding it and you are just reading the signal like this, a row signal, it may be looking something like this. Okay, and it is not actually based on frequency, it is on the time scale. You might be having something like this, and you know you cannot decode it. Okay, you have to decode it using a computer program. Okay, and then what happens is on this particular spectrum, Fourier transform calculation is carried out. So Fourier transform calculation, and once you actually get the Fourier transform calculation, you will finally be having a graph between, let's say, transmittance. It's not only transmittance, you can get it for absorbance also. And then on this side, you'll be going to have 1 divided by lambda, which is mu bar, okay, or the wave number. So if you do this, you are going to get a might be something like this, which I've shown you in the first slide. Okay, so might be you can get something like this. So these are the components that you are basically going to get. Okay, so you use a Fourier transform to convert this from one scale, that means time scale, to the frequency scale. That is usually what Fourier transformation does. Okay, so this is basically called as the interferogram. Okay, this is your CPU, the central processing unit. Okay, and this is the Fourier transform spectrum. So spectrum, maybe I can just write it down as Fourier transform. Okay, so we can also take up the background noise. Okay, so if we do this background spectrum, it can be removed. Okay, background spectrum without sample is taken. If we don't take the sample, and we can actually have a background sample spectrum, sorry. Okay, and it can actually remove instrumental noise. So you can have a noise because of the instrument or because of the properties around the surroundings. Okay, instrumental noise. So this is actually a very simple idea of using FTIR spectra. You will understand it much better when you practically do experiments and try to analyze the results of an FTIR spectra.